Good morning. Myself, Prabha Arunje, working as an assistant professor in EC department at SNS College of Technology. Today, we are going to study an important topic in state variable analysis called controllability and observability. These two concepts help control engineers to answer two important questions. First question is, can we control the system? And second question is, can we observe or understand the system's internal conditions? By the end of this session, you will be able to define controllability and define observability and explain their significance and apply this concept in practical control systems. Yeah, let's begin. Just imagine you are a control engineer. Your job is to ensure that a system performs correctly and safely. To do that, you need to understand what is happening inside the system. The challenge is a control engineer cannot always see everything happening inside a system. Therefore, engineers need tools to understand and control system behavior. Controllability and observability act as the engineer's eyes and ears for understanding system behavior. Observability answer the following questions. Can I determine the internal condition of the system from its outputs? For example, suppose you measure the temperature outside a furnace. Using the measurement, can you estimate what is happening inside? If yes, the system is observable. Next is controllability. Controllability answer the questions. Can I improve system to a desired condition using a available inputs? For example, if you adjust a valve and change the water flow rate to desired value, the system is controllable. Now, let us define the problem. Step 1. Identify the problem. Before controlling any system, we must know what needs to be controlled, which input affects it. For example, temperature, speed, pressure, position. And step 2 is state variables. State variables describe the current condition of a system. Example, position, velocity, current, voltage. These variables help predict future behavior. And the third thing is controllability check. Engineers ask, can the system move from the present state to the desired state? For example, can we increase room temperature from 25 degrees Celsius to 30 degrees Celsius using a heater? If yes, the system is controllable. And last thing is fourth thing is step 4 is observability check. Engineers ask, can we estimate all internal state using measured outputs? For example, can sensors tell us exact pressure inside the tank? If yes, means the system is observable. Now we start thinking about possible control strategies. First one is pole placement, observer design, and LQR optimization. Poles determine system performance. By selecting suitable pole location, we can achieve faster response, better stability, and reduce overshoot. This possible only if the system is controllable. And second thing is observer design. Sometimes all state variables cannot be measured directly. For example, in an aircraft, internal states may not be measurable. In such situation, we use an observer. An observer estimate the unknown states. LQR optimization. LQR stands for linear quadratic regulator. It helps determine the best control signal. The goal is high performance and minimum control effort. By understanding controllability and observability, engineers can develop many controller designs and estimation techniques. Think of controllability and observability as the DNA of a control system. Just as DNA describes a living organism, controllability and observability describe the capability of the control systems. Let me do one small classroom activity. Here you can see the question on your screen. Your job is to find value of the question mark position. After planning the controller, engineers create models, that is, structured state space models and simulation environment and influence score analysis. State space models help represent system behavior mathematically. These models help analysis stability, performance, controllability, and observability and simulation environment. Before implementing a controller in real hardware, engineers test it using software like MATLAB and Simulink, all those things. And influence score analysis, engineers study how input affect states. This helps to understand complex systems more effectively. Now we verify whether the controller works correctly. First is separation principle. The observer and controller can be designed separately. Later they can combine together. This simplifies the design process and optimal experimental. Engineers perform experiments to improve system accuracy. Best experiments leads to better model and fault detection. Observability helps identify fault. Now let us revisit the definition. Controllability is the ability to move a system from one state to another desired state using suitable control inputs. Observability is the ability to determine the internal state of a system from output measurement. Easy example, consider an AC room. Controllability: when you increase AC settings, the room temperature changes. Therefore, the temperature is controllable. Observability: when you read the thermometer, you know the room temperature. Therefore, the temperature is observable. Modern systems are becoming increasingly intelligent. For examples, robots, drones, self-driving cars, and smart factories. These systems require predictable systems, robust systems, interpretable systems. What is meant by predictable systems? The system should behave as expected, that is called predictable system. And robust system means the system should tolerate disturbances, that is called robust system. Engineers should understand system behavior. Controllability and observability make all these possible. Now we are in the assessment quiz part. Let us check your understanding through this assessment quiz. Here we have two assessment quiz. First one is controllability, refers to the ability of a system to which option is correct. Option B is correct. Reach any desired state using suitable inputs. And second question is observability, refer to the ability to which option is correct. Option C is correct. Determine internal states from output measurements. First question, option B is correct. Second one, option C is correct. If you have any doubt, you can ask me through the comment. We will meet in next video lecture. Thank you.